Hello, my name is Polly Fahe and I'm going to talk about some recent work, which is joint work with Isolde Adler, where we introduce a new property testing model, which is a variation of the bounded degree model. So as an outline of this talk, I'm going to start with an introduction to property testing. I will then formally define the bounded degree graph property testing model, and then our model. I will then discuss some results comparing these two models before showing a result on constant time testers in our model, and then concluding with some future work. So our aim is to analyse the structure of graphs efficiently. So we might want to find out if some given graph has some global property. For example, is it connected or is it bipartite? And we want to do this quickly and efficiently. Now, what do we mean by efficiently? Well, traditionally, by efficiently we mean algorithms that run in polynomial time. But what if the graph is huge? What if it's so huge that we cannot even read the whole graph once? And therefore, even linear time algorithms are too slow. And we know that these huge graphs do appear in practice, for example, in social networks and biological networks. And so it's very important that we develop efficient algorithms which are suitable for these huge graphs. And so for huge graphs, by efficient, what we actually mean is we mean algorithms that run in sublinear or even constant time. Now, of course, if we aim for sublinear time algorithms, then we cannot even read the whole graph once, and so we know we're going to have to sacrifice some accuracy. And property testing provides us with a framework to develop these super efficient algorithms whilst providing probabilistic guarantees on the quality of the output. So let's say we have some set of possible inputs, and then we have a property defined on that set. Normally what we want to do is we want to decide whether a given input has the property or whether it doesn't have the property. Now, in property testing we relax this slightly, and we define a distance measure from an input to the property, and then our aim is to decide with high probability whether the input has the property or if it's far away from having the property. And if it's close, we don't mind what we output. Now, property testers, they typically work by looking at a constant number of small local parts of the input, and then by what they see, they try and decide if the input has a property or is far away from having a property. So let's just go through a very brief history of property testing. It was first introduced in 1996 by Rubenfeld and Sedan in the context of program checking. Shortly after, it was extended to testing properties of dense graphs by Goldreich, Goldwasser and Ron. And then shortly after that, the bounded degree property testing model was introduced by Goldreich and Ron, and this is the model which is what we're going to be interested in today. So property testing has been around for over 20 years now, and since then there has been much research on what properties are testable in various different models and for various different objects. So for example, there's a model for general graphs, which is suitable for graphs that are not necessarily dense, nor have bounded degree. There is also work on property testing for relational databases, and in fact everything that I will discuss in this talk can be easily extended to relational databases. So before I formally describe the bounded degree property testing model, let me just note that in this talk all graphs are finite, undirected, and do not have loops and multiple edges. The degree of a vertex is the number of edges incident to it. The degree of a graph is the maximum degree of its vertices. And finally, a class of graph C has bounded degree D if all graphs in the class C have degree at most D. So let us now define the bounded degree property testing model. So the input class C is just some set of bounded degree graphs, and then a property is just a subset of the input class. And just to note, we always assume that properties are closed under isomorphism. And so as I mentioned earlier, we need to define a distance measure from the input graphs to the property. So let us start by defining the distance between two graphs. So the distance between the graphs G and H is the minimum number of edge modifications that are needed to make G and H isomorphic, where an edge modification is just adding or removing an edge. We then say a graph G is epsilon close to the property on the input class if there exists some graph H in the property, which is at distance at most epsilon times D times the number of vertices in G, where epsilon is some small number between 0 and 1, and D is the degree bound. Then if a graph is not epsilon close, we say it's epsilon far. An epsilon tester is then a probabilistic algorithm which is given oracle access to a graph G from the input class C, along with a number of vertices in G. And I'll come back to what I mean by oracle access in a second. So then the algorithm accepts G with probability at least 2/3 if G has the property, and rejects with probability at least 2/3 if G is epsilon far. So what did I mean by oracle access? Well, the algorithm can make queries of the form Vi to the oracle, where V is a vertex and I is some number between 1 and the degree bound. The answer to the query Vi is then the ith neighbour of V in the graph, and if V has less than I neighbours, a special symbol is returned to indicate this. And we assume that oracle queries can be answered in constant time, and therefore with these types of queries, a fixed radius neighbourhood around a given vertex can be explored in constant time. We then say that the query complexity of a tester is the maximum number of oracle queries made with respect to the number of vertices in the graph. And then we say that a property is uniformly testable on an input class C if for every epsilon between 0 and 1 there exists an epsilon tester for P on C which has constant query complexity, and we note that we require this tester to work for any size graph. The time complexity of a tester is as usual, it's with respect to the number of vertices in the input graph, and I just want to note here that in a lot of the work on property testers, the main aim is to develop testers with constant query complexity, and sometimes authors they don't even mention the running time, but of course the running times of the algorithms is important, especially in view of applications. Okay, so just before I introduce our model, let me just note that throughout this talk, I'll refer to the model I've just introduced as the classical model, and then the model I'm just about to introduce I will refer to as our model or the new model. Okay, so in our model, most of the definitions from the classical model, they do carry over, and our model differs in two ways from the classical one. So firstly, in our model, the distance between two graphs G and H is the minimum number of edge and vertex modifications that are needed to make G and H isomorphic. Where again an edge modification is just adding or removing an edge, and a vertex modification is adding or removing a vertex, where if we remove a vertex, then we remove all edges incident to it. And secondly, we now say that a graph G is epsilon close to a property P on the input class C if there exists a graph H with a property such that the distance between G and H is at most epsilon times D times the minimum number of vertices in G or H. So now in our model we can compare graphs on a different number of vertices. So let us look at an example. So if we take the following two graphs, G and H, where H is from G by just removing a corner vertex, then the distance between them in the classical model is infinity because they are on a different number of vertices, and so by edge modifications alone we cannot make them isomorphic. But in our model, the distance between them is 1 because we can just remove a corner vertex from G to make it isomorphic to H. And we were surprised that this model hadn't been studied before. So for example, let us take two large graphs that are isomorphic, and then let us add an isolated vertex to one of these graphs. And these two graphs, they look locally nearly identical, and so we argue that it makes sense that these two graphs should have a small distance from each other. But in the classical model, they would have distance infinity. So one of our first questions when we started studying this model was, how does our model compare to the classical model? And it's easy to see that for any input class C and property P on C, if P is uniformly testable on C in the classical model, then P is also uniformly testable on C in our model with the same time and query complexities. So why is this? Well, if we let pi be an epsilon tester for P on C in the classical model, then we can also show that pi is an epsilon tester for P on C in our model. So let us discuss why this is. So let G be a graph from the input class, then we need to look at two cases. The first case is when the input graph has the property, and in this case pi will clearly accept with probability at least 2/3, as pi is an epsilon tester for P on C in the classical model. The second case we need to consider is when the input graph G is epsilon far from P in our model. If G is epsilon far from P in our model, then it must also be epsilon far from P in the classical model, as if G requires many edge and vertex modifications to make it have the property, then it clearly also needs many only edge modifications to make G have the property P. And in fact, if the input graph G requires a vertex modification to make it have the property, then it's not even possible to make G have the property with only edge modifications, and hence G is epsilon far from P in the classical model. So clearly pi will reject with probability at least 2/3 as required, and hence pi is an epsilon tester for P and C in our model, and hence P is testable in our model. Okay, so we have shown that any property that is testable in the classical model is testable in our model, and so the next natural question is whether there exists a property that is not testable in the classical model but is testable in our model. And we have come up with such a property. So we show that there exists a property on the class of all bounded degree graphs that is trivially testable on the class of all bounded degree graphs in our model, but is not testable on the class of all bounded degree graphs in the classical model. Okay, so let me describe this property. So if we let P be the property that contains all graphs with bounded degree that are bipartite or have an odd number of vertices. So in our model, any graph from the input class has distance at most 1 from the property, because if the input graph is on an even number of vertices, we can just insert an isolated vertex. Therefore, if we assume that the number of vertices in the input graph is larger than some constant number, then the tester can just always accept. And otherwise, if the input is on a small number of vertices, we can just do a full check of the input graph. Hence, the property P is testable in our model. In the classical model, however, if the input graph is on an even number of vertices, then we must test whether the input graph is bipartite or far from being bipartite. But Goldreich and Ron proved that in the classical model, bipartiteness cannot be tested with query complexity little o root n, where n is the number of vertices in the input graph. And so if you remember back to the definition of testability, we require a constant number of queries for testability, and hence P is not testable in the classical model. And we note that we can replace the property of being bipartite by any other untestable property in the classical model to obtain more examples of properties that are testable in our model but are not testable in the classical model. Okay, so we have seen that our model is stronger than the classical model in the sense that any property that is testable in the classical model is testable in the new model, but the converse is not true. So another interesting question is, are there properties that are testable in the classical model, but have faster running times in our model? So Isolde Adler and Frederick Hoff, they show that every property that is definable by a monadic second-order logic with counting sentence on the class of all bounded degree and bounded tree width graphs are uniformly testable on that class with polylogarithmic running time in the classical model. Now, it's not known whether this running time here can be improved to constant time, but what we can show is that in our model, these properties are testable in constant time. So we show that every property that is definable by a monadic second-order logic with counting sentence on the class of all bounded degree and bounded tree width graphs are uniformly testable on that class with constant running time in our model. Now, why are we interested in these properties? Well, there are many well-known graph properties that can be defined by a CMSO sentence. For example, subgraph freeness, bipartiteness, colorability, even-hole freeness, and Hamiltonicity, for example. And so we know that we can test all of these properties in constant time on graphs with bounded tree width and bounded degree in our model. And I'm just now wanting to give you a very brief idea of how we prove this, but before we do that, I just need to define neighbourhoods. Okay, so given a graph G and a vertex V from G, the R neighbourhood of V is the tuple that contains the subgraph of G induced by all the vertices at distance at most R from V, and then V itself. So let us look at a quick example. So if we take the following graph, then we can see that the vertices I, J, C, B and E are all at distance 2 from the vertex V. And so the 2 neighbourhood of V in this graph would be the tuple HV, where H is a following graph. An isomorphism equivalence class of R neighbourhoods is called an R neighbourhood type, and the number of R neighbourhood types we denote by CR. The R neighbourhood histogram of a graph G is the vector with CR components, which is indexed by the R neighbourhood types, where the component corresponding to a type tau contains the number of vertices in G which have R neighbourhood type tau. We then say that the R neighbourhood distribution vector of a graph G is the R neighbourhood histogram vector of G divided by the number of vertices in G. Okay, so let me give you an idea how we prove our result, that every property that is definable by a monadic second order logic with counter centers on the class of all bounded degree and bounded tree width graphs are uniformly testable on that class with constant runtime in our model. Okay, so let P be a property that is definable by a CMSO sentence on the class of all bounded degree and bounded tree width graphs. Then we can use that P is hyperfinite, which is because it is known that the class of all bounded degree and bounded tree width graphs are hyperfinite. And then we can also use a previous result that says that the set of R neighbourhood histograms of the graphs in P have a simple structure. Okay, so then we can use these to show that there exists an R such that for any graph G from the property P, there exists a constant size graph G prime whose R neighbourhood distribution vector is close to G's. But this is not true for any graph that is far from P. So now to construct a tester for P, all we have to do is use a previous result from Newman and Sola that says that in constant time and with a constant number of oracle queries, we can compute an estimate to the R neighbourhood distribution vector of the input graph, such that with high probability this estimate is a good estimate. And then all we have to do is compare this estimate to the R neighbourhood distributions of small constant size graphs from the property to decide whether the input graph has the property or is far away from having the property. And clearly this can be done in constant time. Okay, so let us conclude with a discussion on some future work. So in the future it would be interesting to find other examples of properties that are testable in our model, but that are not testable in the classical model. It would also be interesting to know whether properties expressible in CMSO on graphs of bounded degree and bounded tree width can be tested in constant time in the classical model also. And finally, a future challenge is to obtain a characterization of properties that are testable in our model. Now this is no easy task, and maybe a good starting point would be to see if known characterizations from the classical model carry over to our model. So we know that one direction will carry over, but does the other direction also? So thank you for listening.